In this lecture, we are going to study the inverting amplifier, and we will do this using an examination question. In this question, we are told that the circuit of an inverting amplifier incorporating an ideal operational amplifier is as shown in that figure 8.1. Explain why point P is known as a virtual earth. B. Derive an expression in terms of R1 and R2 for the gain of the amplifier circuit, explaining your working. Part 3. A relay and an output terminals of the amplifier circuit are shown in figure 8.2. On figure 8.2, show how the relay may be connected to the amplifier output so that the relay operates only when Vout is positive. So let's start with the first question. In this question, we are asked to explain why point P is known as a virtual earth. This point here is referred to as the virtual earth. We know that for the amplifier not to saturate, the difference between the two inputs, the inverting input and the non-inverting input, must be very small, very, very small. That is the first point. The second point is that we observe that the non-inverting input is 0 volts because it is connected to the earth line. Since one of the inputs is 0, and the fact that the difference between the two inputs must be very, very small, it means that this inverting input must be very close to 0. I will repeat that because it is very important. The difference between the two inputs must be very small for the amplifier not to saturate. One of the inputs, which is the non-inverting input, is connected to the earth line. That is, the non-inverting input is 0 volts. Now, given that the difference between the two inputs must be very small, it follows that the inverting input must be very close to 0. Very, very close to 0. And since it is very, very close to 0, it appears as if it is 0 volts. The inverting input must be 0 volts. Now we see that point P, the potential at point P is actually the inverting input. So point P must be at a potential which is very close to 0, that it appears almost to be equal to 0. And that is why it is referred to as a virtual earth. Virtual means it appears to be as if it is earthed. It appears as if it is 0 volts. So these are the 3 points. The first one is that for the amplifier not to saturate, the difference between the two inputs must be very small. The second point is that the non-inverting input is earthed. This one here. That is, it is 0 volts. Since the non-inverting input is maintained at 0 potential, then for the difference between the two inputs to be very small, the inverting input must be very close to 0. So the potential at point P is so close to 0 that it appears to be 0. Those are the 3 points which are required for the 3 marks. Let's go to part B, where we are required to derive an expression in terms of R1 and R2 for the gain of the amplifier circuit, and we have been asked to explain our working. So from part A, we have just agreed that the potential at point P is 0, so it is 0 volts. 0 volts. Let's suppose that the input is positive, so positive V in. So the potential at this point is higher than 0. So current through R2 will flow this way. This current, we are going to call it I through R2. Flows that way. in any one circuit, when we get to a junction, current is meant or it is supposed to split. So we expect this current to split in such a way that there will be some current which flows in this direction and some current which flows in this other direction. At this point, we remember one of the properties of an ideal operational amplifier. And this property is that an ideal operational amplifier has infinite input impedance. That means that the resistance to the input is so high that the amount of current which flows into and out of any one of these two inputs is zero. That's a very important point. Since the input impedance, that is the input resistance, is so high, the current which flows into and out of any one of these two inputs is zero, meaning that this current, I2, which flows towards this junction, all of it takes this route. So this current and this current are the same. That means when we consider the current which flows through R1, which we can call IR1, the two currents must be the same. So that is where we start from. We say that IR2 must be equal to IR1. But we must remember from Ohm's law, current is given by potential difference divided by the resistance. Current through any resistor is equal to the potential difference across that resistor divided by the resistance itself. For example, here we are talking about current through R2. So this current through R2 is equal to the potential difference across R2 divided by R2 itself. So how do we get the potential difference across a resistor if the potential at this point and the potential at this point is given? First of all, we look at the direction of flow of current and we reason out, since current is flowing in this direction, the potential at this point is higher than the potential at this point, because current always flows from a point at a higher potential to a point at a lower potential. That means that if we want to get the potential difference between these 2 points, that is the potential drop across R2, we do the higher potential minus the smaller potential. So here we are going to get V in minus 0 divided by R2. V in minus 0 gives us the potential drop across resistor 2. And when we divide that potential drop by R2 itself, we are getting the current through it. That one is very important. And this one is equals to IR1 is equal to the current through R1. Now current is flowing from this point which is at 0 potential, so 0 must be higher than the potential at this other point here, which is V out. The potential at this point is V out. So the potential across R1 is 0 minus V out. Of course, because we are calculating that current through R1, we divide by R1. Now this implies that V in minus 0 is just V in divided by R2. 0 minus V out is minus V out over R1. And we are almost coming to the end of this derivation, because at this particular point, because we are looking for the gain of the amplifier, we remember that the gain of an amplifier is always given by V out over V in. So we bring our V in here and our R1 comes here so that I can get the ratio V out over V in. So this implies that our R1, there's an implication sign, R1 over R2, remember I've just shifted my R1 there, or multiplied both sides by R1 and then divided both sides by V in. So it's going to be equal to minus V out over V in. Now this further implies that V out over V in, which is actually equal to our gain, the gain of the amplifier, is equal to, we can multiply both sides by the negative sign because I want this side of the expression to be free of the negative sign so that I can just get V out over V in, which I call the gain of the amplifier. So when I multiply both sides by the negative, that negative comes here and it multiplies the ratio of R1 over R2. And you can see that the gain of the amplifier is given by minus R1 over R2. And actually, we have answered the question. We have derived an expression in terms of R1 and R2 for the gain of the amplifier. So we can say the gain A is equal to minus R1 over R2. R1 actually happens to be the feedback resistor. This is the feedback resistor, RF. The minus sign implies that the input is out of phase with the output. So that if, for example, the input is like this, the output will be out of phase with it, and it will be like that. Although it's going to be amplified, but it will be 180 degrees out of phase. You just need to look at the way this wave starts. It starts with a crest. This other one will start with a trough, showing that the two are out of phase by 180 degrees. That's what the negative sign implies, that the output is out of phase with the input. So for example, if the input is positive, the output is going to be negative, and vice versa. If the input is negative, the output is going to be positive. Now let's go to part 3, which requires us to do something about a relay. We are told that a relay and the output terminals of the amplifier circuit are shown in figure 8.2. So let's go to part C. And here we are in part C. We have this relay. This is the electromagnet, while this is the switch itself. A relay is a device which is used to, like for example, you can have a small amount of current controlling a large amount of current. So this is the circuit that has got a large amount of current, and this other circuit here will have a small amount of current, and it is the one which is meant to be connected to the amplifier because the current from the amplifier might be very, very small. So the coil of the relay is connected to the amplifier, like we are going to see in a short while. On figure 8.2, show how the relay may be connected to the amplifier output so that the relay operates only when V out is positive. When this V out is positive, in other words, this section is positive. This means that the relay is not meant to work if the output is negative. And here we remember a certain special device, which is the diode. The diode will only allow current to flow in this direction. That means when the V out is positive. And therefore you're going to have a diode here, and we're going to connect the electromagnet to the output and the other terminal connected to 0 volts or connected to the earth line at this particular point, like this. So we have our diode here, and when the V out is positive, this diode will allow current to flow in this direction and the relay will work. But when the output is negative here, meaning that current is meant to flow this way, this diode is going to block that current and the relay will not work. Of course, the other section of the relay is connected to the 0 volt line or the earth line, like I've just explained. So for you to earn these 3 marks, you need to show that kind of connection. A diode, and it should point in the correct direction so that we obey this instruction here. The relay only works if the V out is positive. If it was such that the relay will work if the V out is negative, then this diode will point in the other direction. And it is just as simple as that. So this is one of the examples of questions which involve an inverting amplifier, and you can see it is very easy to get all these 9 marks so long as you remember those important points.